Hi everyone. Today we are going to cover Chapter 8, the long run and short run cost curves. So this is the overview of today's presentation. First we will derive the long run cost curves, and we will also similarly derive the short run cost curves. We will then show what happens when the input prices changes. We will define the average cost and the marginal cost, which are similar concepts to, say, average products and marginal products, or average utility and marginal utility. We will also introduce the concept of economies of scale and diseconomies of scale, and we will make a comparison between those to the returns to scale that we learned previously. Those concepts are closely related. After we derive our short-run cost curves, we will show the relationship between our short-run cost curve and the long-run cost curve. We will similarly define the average short-run total cost and marginal cost. And lastly, we will show the relationship between the short-run averages, the short-run marginals, to the long-run averages and the long-run marginals. So you probably have realized there are going to be a lot of concepts in this chapter, and to have an example that is consistent, I'm going to use this example. So I encourage you to pull out a paper or either take a screenshot of this, write down this example, so that whenever I introduce a new concept and I use this example to illustrate, you can write it down, and you can always have this piece of paper with you throughout today's video. So we are going to consider a production function that is Q equals to L times K to the power of a quarter. And we are going to assume that the wage rate and the capital rental rate are the same, both are 1/4. So I'm choosing those numbers to be the same only to make the math simpler. They don't carry any specific meanings. So we kind of already did or derived the long run total cost curve last time, if you remember, when I used the most general Cobb-Douglas production function, and I didn't substitute any numbers, but I used all letters, and I derived a very complicated looking expression for both the optimal combination of inputs, or the number of labor and the number of capital that the firm is going to use to minimize its cost, as well as the total cost. We can write the total cost as a function of all of our parameters, our A, alpha, beta, Q, W, and R. The expression is messy, but the idea is already presented there. So the total cost curve, or the long run total cost curve, tells us the relationship between the minimized long run total cost and the quantity of output. So we emphasize that the total cost here is the minimized total cost. So it tells us that if the firm wants to produce Q units of output, what is the minimum amount of cost the firm must have to pay. So this is, as I was saying, based on the idea that we can solve this general problem. So for any given production function under the wage rate and the capital rent, we can solve this problem. We can write our optimal input combination, that is L star and R star, as a function of the parameters that are given to us, right? So we can write L star as a function of Q, W, R, and K star as a function of Q, W, R. And here I'm implicitly already fixing our production function. And with the L star and K star, we can write our long run total cost. That is going to be W times L plus R times K. And we substitute our L star and K star into the expression. So our long run total cost is W times L star, which is a function that depends on Q, W, and R, and R plus R times K star, and again, it depends on Q, W, and R. And if we look at fixed value of W and R, we can see that this long run total cost simply changes when Q changes. So we can write this as a function of Q. And this is the long-run total cost function. And the graph it corresponds to is our long-run total cost curve. This is the idea how we derive this concept from our cost minimization problem. So for this function, it must be increasing in Q. If the firm wants to produce more units of output in the long run, the minimum amount of total cost the firm must have to pay must be increasing as the quantity increases. And also, if the firm produces zero units of output in the long run, and because we say in the long run, if you remember in the last chapter, we were saying that, well, long run and short run refers to the length of period of time where the firm have different degree of flexibility in adjusting its inputs, right? So we say in the long run, the firm has enough flexibility to adjust all of its inputs. And essentially, the firm can choose to use 0 units of all of its inputs if the firm were to produce 0 units of output. Therefore, the long run total cost when the firm produces 0 units of output must also be 0. So for our example, I'm going to go through this process again. We've already done this a few times. So given the production function and the wage rate and the capital rent, we can first calculate the marginal products of labor and the marginal products of capital by taking the partial derivatives. We can then calculate the marginal rate of technical substitution, and that is negative K divided by L. And because this is a Cobb-Douglas production function, we can use the tangency condition. And we equate our MRTS to the slope of our iso-cost line. And the slope of those is negative W divided by R. And this gives us the equation, the optimal ratio, that is K equals to L. So we know that the optimal ratio of the input combination for the firm is to choose the same amount of labor and capital for the given production function and the wage and capital rent. In the second step, we substitute this optimal ratio into the production function. So we have Q equals to L times K to the power of a quarter. We substitute K equals to L into it. So, and we can solve for L. So we solve that L star, the optimal amount of labor the firm would want to employ, is equal to Q squared here. And we see that this L star is a function that depends on Q, and implicitly it depends on W and R as well. But because W and R are numbers, we have evaluated them. They eventually became a coefficient of 1 in front of Q squared. So with this L star, we substitute it back into our optimal ratio. So K star must also be the same as L star, that equals to Q squared. And here the K star is also a function that depends on Q and implicitly W and L. And in the last step, we can write our long run total cost as W times L star plus R times K star. And we have W and R both being 1/4, and L star and K star both being Q squared. So our long run total cost as a function of Q star is going to be half times Q squared. We see that this function is, first of all, increasing in Q. As Q becomes larger, Q squared becomes larger, the long run total cost becomes larger. And secondly, if we substitute Q equals to 0 into this function, we see that the function takes the value of 0 when Q equals to 0. So it is those two must be satisfied for our long run total cost functions. And as long as we did our derivation correctly, those two will be satisfied. So here I'm going to draw a graph first, and I'm going to show later on that what happens when the input prices changes. So the conclusion I've already put in here that it is that when the input prices increases or decreases, it will rotate our long-run total cost curve. So here it's actually not put very well. I'm going to change this on the slide I upload to iLearn. So it should actually be, yeah, let me just cross out this part. So whether it is going to rotate upward or downward depends on if the input prices increases or decreases. All right. So I think what I had in mind is that when input prices increases, it is going to rotate it upward. But I only put a change there. So we are going to draw two graphs together. And I'm going to label the axis so that you know what are we drawing here. So on this first graph, we have labor and capital. So this is the cost minimization problem that we solve for the firm. And on the second graph, we have our quantity and our total cost. So this is the total cost curve, or the relationship showing our total cost with the amount of quantity that the firm produces on the second graph. So I'm going to start by picking a random amount of quantity. Here, let's say this is our Q1. And for this value of Q1, we can draw the corresponding isoquant on our left panel, right? So we can draw an isoquant. And let me use the blue color, I think. And let me use the blue color here as well. We can draw the corresponding isoquant on the left panel. So that might look something like this. And this is our isoquant that Q equals to Q1. Well, we already knew we can solve this cost minimization problem by finding the isocost line that is tangent to the isoquant. And let's say the isocost line looks like this. So this is the isocost line that incurs a total cost of TC1. The point over here is our cost minimization input combination, but we are not drawing this on the right panel. Anyway, so if this is our solution and TC1 is our solution over here, well, we can find the corresponding value of TC1 on the right panel, right? So let's say this is the level of TC1. Then we can mark this point. So we know this point will be on our total cost curve. Because when the firm is to produce Q1 units of output, and solve the cost minimization problem, the minimum amount of the cost the firm has to incur is TC1. And this is exactly what our total cost or our long-run total cost curve is showing us. So if the firm were to produce at a higher level, for example, Q2. So let's pick another random point that is Q2 over here. Well, we can draw the isoquant here corresponding to Q2 as well. So perhaps this is the isoquant corresponding to Q equals to Q2. We can again solve the cost minimization problem of the firm. And we are finding the isocost line that is tangent to our isoquant. And also, because the input prices haven't changed yet, so the two isocrossed lines are going to be parallel to each other. So if this is the isocrossed line that is represented by TC2, then we know on the right panel, we can mark this second point. That is going to be our TC2. And we know that this point must also be on our cost curves. So if we connect those points, we can do the same exercise for every level of Q, right? For every value of Q that we have on this horizontal axis, we can do the same exercise. We can find the corresponding level of TC. And if we connect all of those points, this is our long-run total cost curve. And mathematically, we are writing this down as a function. And graphically, this is how we can derive it. Now, let's suppose if the price of an input changes, and more specifically, let's suppose W increases. Because what I had in mind when I prepared the slides is that W increases. So we know that it's going to rotate it's going to rotate our total cost curve upward, but I'm going to show you how does that work. So let's see. Now, if W increases, well, it doesn't change the isoquant corresponding to Q1 and Q2. Those two remain in the same place. It is going to change the isoquant, however. The new isoquant, when W increases, is going to become steeper. And for the same value of TC1, it's going to become a steeper isocrossed line. And if the firm will continue to use TC amount of total cost, we can see that the firm is no longer able to produce Q1 units of output, right? So no point on our TC1 isocrossed line touches our isoquant Q equals to Q1, because now the price of labor becomes more expensive. So the new point that solves our cost minimization problem is, so I've probably drawn this too steep. Let me modify this a little bit. All right, it still becomes steeper, but not as much, so that I can draw the graph. Let me see which one. All right, like this. So this is our TC1. So, well, the firm is still going to solve the cost minimization problem when it is going to produce Q1 units of output. So how does the firm do it? The firm, well, again, finds the isocrossed line that is tangent to the isoquant. The new point is probably going to look happen at here. So the new optimal point is potentially this red point I marked. The firm is going to substitute some of its labor with capital, because labor is now becoming more expensive. And this new line is called TC1 prime. And we know because it is higher than TC1, TC1 prime is going to be larger than TC1. So what corresponds on the graph is that when the firm is due to produce Q1 units of output, the total cost the firm must incur is no longer TC1, but a higher level, at a level that is higher than TC1. And let's say this is where TC1 prime is. So instead of the blue point previously, now the firm, to continue to produce Q1, it must incur TC1 prime. So the total cost curve will pass through this point. Now, similarly, when we have TC, if we look at TC2, the new isocost line for TC2 is going to have the same slope as those TC curves. So this is the new TC2, and again, it no longer touches our Q equals to Q2, right? So the firm, to solve its cost minimization problem, has to move to a higher isocost line, that is potentially here, and use this new optimal input combination, that is this point I'm marking now. And similar, for the same reason, because labor becomes relatively more expensive to capital, the firm is substituting away some labor with capital. So the firm is moving from that point to the new point. And for this new line, we call this TC2 prime, because this is also higher than TC2. We know that TC2 prime must be larger than TC2. So on the graph, the new point of TC2 might be somewhere here. So now, instead of the original blue point, this red point is on our new TC is on our new long run total cost curve. Well, to derive or to draw the new long run total cost curve when the price increases or when the price changes, we are still going to connect all of those points. And if we do that, we will realize that the new total cost curve may look something like this. So of course, my drawing is not showing that it is actually the same. It's a rotation. But we can see that first, they are both still increasing, and they take the value of 0 when we produce 0 units of output. Those two must be satisfied. And we can't actually show that it is a rotation graphically, but if we calculate mathematically, we will see that it is a rotation. And by rotation, it is basically that basically we are rotating the blue line by a certain degree to become the red line. And we call this rotate upward. So so whenever it is an increase in the input prices, it's going to rotate our long run total cost upward. When there is a decrease in the input prices, it is going to rotate our long run cost curve downward. So if input prices decreases instead of increases, and on the graph, it may be represented by things like this if the input prices decreases, all right? And of course, this also depends on the original shape of our total cost curve. And they do not necessarily look like what I'm drawing over here, but I'm just trying to show you what happens when the input prices changes. So here is the extra credit question, the second one for this week. So let's say the firm has a production function that uses 2 inputs, And let's, so here I didn't specify what type of production function it is. It can be any arbitrary type of production functions. And let's suppose the prices for both inputs increases by 20%. And we are asking what will happen to the minimized long-run total cost. So will it increase by more than 20%? Will it increase by exactly 20%? Will it increase by less than 20% or possibly decrease? Or will the answer depends on what the type of the production function it is? You can think about this and provide your answer on iLearn. So for the cost function, we can similarly define the average cost and the marginal cost as we did in defining the average product and the marginal product, all right? So the average cost is going to be the total cost divided by the quantity, and the marginal cost is going to be differentiating the total cost with respect to quantity. And graphically, it is the slope of our total cost curve. I mean, the marginal cost is the slope of our total cost curve. And in our example, we calculated previously that our total cost is half times Q squared. So based on this definition, our long-run average total cost is half Q, or Q divided by 2, and our long-run marginal cost is to differentiate our half Q squared with respect to Q, and that gives us Q. So we can see those two are not necessarily the same. They are generally different in most cases. In some special cases, they will be the same. And here is a interesting relationship between the average cost and the marginal cost. And actually this relationship holds for anything that is the average of a function and that the other a marginal of a function. So this holds true for the average product and the marginal product. This holds true for the average utility and the marginal utility as well. But back then, I think this concept wasn't really relevant, but here it is. When we were talking about cost, the absolute value of the cost is important, so this concept becomes relevant. So this fact is saying that if the average cost is increasing, then the marginal cost is higher than the average cost. Or we can flip the order. If the marginal cost is higher than the average cost, then average cost is increasing. On the graph, this corresponds to this area, right? So here we can see that our marginal cost curve, the blue line, is always higher than our green line, which is our average cost curve. And over this region, our average cost curve is increasing as Q increases. Now, on the other region, that is when our marginal cost is smaller than our average cost. So that corresponds to this region. So our blue line is always below our green line. And over this region, we can see that our average cost is decreasing. So the green line is decreasing over this region. And lastly, the marginal cost, at this point, when those two lines intersect, it is the minimum point of our average cost curve. Because to the right of it, it is increasing. So every point to the right of it is higher than point A. And to the left of it, it has been decreasing. So again, every point to the left of it is higher than point A. So point A is the smallest point of our average cost curve. And this is the point where our marginal cost curve intersects our average cost curve. So we can think of this using your GPA as an example. So if you think your cumulative GPA as your average GPA or the average, and your GPA this quarter is your marginal GPA, all right? So the GPA you get this quarter is like the additional you get, and your cumulative GPA is the average of your past. If your GPA this quarter is higher than your cumulative GPA, this means that your cumulative GPA will increase after this quarter, right? So when your GPA this quarter, that is your marginal cost, is higher than your cumulative GPA, that is your average cost, then the average cost or the cumulative GPA will increase. And conversely, if your GPA this quarter is lower than your cumulative GPA, then your cumulative GPA will decrease. So when the marginal is smaller than the average will decrease. And lastly, if your GPA this quarter happens to be the same as your cumulative GPA, then your cumulative GPA do not change. So when MC equals to AC, we are looking at a point where the AC is not changing. So at this minimum point, the derivative of our AC curve is 0. AC is not changing at this specific point. And as I was saying, this is a relationship that is going to hold true because of mathematics. So by the way we define average cost and marginal cost, this relationship will hold true. Next, we are going to introduce two new concepts, economies of scale and diseconomies of scale. So when we look at the average cost curves, we think that there are three regions representing, well, basically all types of average cost curves. A region over which it is decreasing as Q increases, a region over which it is constant as Q changes, and a region over which it is increasing as Q increases. So when the average cost decreases as Q increases, that's saying that as the firm produces more output, the average cost of each unit of output is becoming smaller and smaller. So the firm, in a sense, has more competitiveness in the market, right? And we call this region when the firm enjoys economies of scale over this region. And it is featured by the fact that the average cost goes down as the output increases. So on our graph, it corresponds to the area that is lower than Q prime. So there are different kinds of reasons that this might happen. I'm going to explain one reason, which is the indivisible input. So imagine the firm is to produce or to manufacture a good, and the firm has to purchase or invest in the assembly line. And each assembly line may be capable of producing, say, 5 million outputs in a year. And the assembly line is indivisible. It's not possible to purchase, say, half unit of an assembly line. So if the firm were to produce any quantity lower than 5 million output, the firm would anyway have to invest in the assembly line. That is going to be quite costly. But as the firm increases its output from 1 million to 2 million to 3 million to 4 million to 5 million, the firm do not need to purchase another assembly line, right? So the firm is not going to increase its cost in this indivisible input dimension. It may increase its cost in other dimension of inputs, such as raw materials or labors or management, but at least for this assembly line, the firm do not have to increase its cost. And this might lead to the decrease in the average cost and let the firm enjoy economies of scale. And this may correspond to the region that is below Q prime. Now, beyond certain point of quantity, the firm may suffer from what we call the diseconomies of scale. That is when the average cost goes up as output increases. And on the graph, this corresponds to the region that is above Q double prime. And similarly, there are many reasons that might cause this to happen. One explanation is that the firm may suffer from what's called the managerial diseconomies. The idea is that as the firm produces more and more outputs, the firm would have to hire more and more workers, and the management of the workers, the coordination will become not only more difficult, but will become increasingly more difficult. So, and if the firm were to produce beyond a certain scale, the cost that the firm has to pay for the management, for the coordination, will become increasingly high, so that it will drive up the average cost. The concept of economies of scale is closely related to the return to scale that we learned previously. And I just want to distinguish that economies of scale is a concept for, well, the cost functions. It's based on our average total cost. And the return to scale is a concept for production functions, all right? So, and I'm not sure if you still remember what determines the return to scale for the production functions. If you don't, you can go back to, I think, chapter 6. Chapter 6, that the last part of chapter 6, that's where we described it. So those two are closely related. So whenever the production function exhibits increasing return to scale, the firm will enjoy economies of scale. And basically this means that when the scale of the firm becomes larger, it is more cost efficient. And we did an example in last chapter showing that when we have a single large firm versus 4 small firm, which one is more cost efficient, and that depends on the return to scale of the production function. So here, conversely, if the production function exhibits decreasing return to scale, the firm will then suffer from diseconomies of scale. So when the production function has decreasing return to scale, the more output the firm want to produce, the higher the average total cost the firm will have to incur, and that is diseconomies of scale. So with our running example, this is a special Cobb-Douglas production function. And because the sum of its exponent is 1/4 plus 1/4, that is a half, and that is smaller than 1, we say that our production function exhibits decreasing return to scale, right? And again, I showed why this is the case in previous lectures. So because this production function exhibits decreasing return to scale, we can look at the long-run total cost curve we derived and the long-run average total cost curve that we derived. The long-run ATC is Q divided by 2, and we can see that this is increasing in Q as Q becomes larger. So the long-run ATC is increasing in Q, meaning that the total cost or the firm suffers from diseconomies of scale. And that is because the production function exhibits decreasing return to scale. So moving into short run, we can similarly derive and define our short run total cost function as we did for long run. So similarly, in the short run, the amount of capital is fixed, and we can ask if the firm wants to produce 2 units of output, what is the cost it has to incur? And here we are not solving K bar because K bar is fixed. So we can write our L star, the amount of labor the firm uses, as a function of our other parameters. So we write L star as a function of Q, W, R, and K bar. And actually, it may not depend on W and R, because we know that in the short run, the firm solves for L that satisfies the production function that satisfies that the production function will produce the target level of output, right? And with this L star, we can calculate our short-run total cost, that is W times L star plus R times K bar. And again, if we fix W, R, and K bar, we can see that the only thing that matters in here is Q. And we can write our short-run total cost as a function of Q. Now for our example, again, this production function, for fixed level of K bar, we solve for L star, that will produce Q units of output. So our L star equals to Q to the power of 4 divided by K bar. We can write our short-run total cost being W times L star plus R times K bar. And we have both W and R equals to 1/4. So we substitute L star, W, and R into this expression. We get Q to the power of 4 divided by 4 times K bar plus K bar divided by 4. So this is our short-run total cost function. We can similarly define our average cost and the marginal cost for the short run. So in our example, so they are going to be dividing the short run total cost by Q to get the short run average total cost, and also differentiating short run total cost with respect to Q to get the short run marginal cost. And in our example, we just calculated in previous slide our short run total cost. If we divide it by Q, we get our short run average total cost. If we differentiate it with respect to Q, we get our short run marginal cost. And those two functions, and we can see all of those actually depends on K bar, right? So when the level of capital is fixed at a different level in the short run, our short run total cost, the marginal cost, the average total cost are all going to be different. So we can, and we've also briefly introduced this concept in the last chapter, I believe. So we can distinguish our short-run cost into variable cost and fixed cost. So variable cost is the part of the cost that changes as our output level changes. And the fixed cost is the part that does not change as our output level changes. And if we look at our short-run total cost function equation, this part changes as Q changes, because as Q changes, the L star will change. So W times L star will change. And the R times K bar is the part that does not change. There is no Q in this expression, right? So this is our fixed cost. And the short-run total cost is going to be the sum of our variable cost and the fixed cost. The fixed cost. And I emphasize again here that in the long run, there is no fixed cost because the firm can adjust all of its inputs, and all the costs are going to be variable cost. We can similarly define the corresponding average variable cost and the average fixed cost, as well as the marginal variable cost and the marginal fixed cost. I didn't write it down here, but the short-run marginal fixed cost is going to be 0, because the fixed cost, by definition, is the cost that does not change as Q changes, right? So if this is a constant and we take the derivative with respect to Q, we are going to get 0. And the short-run marginal variable cost is just going to be the same as the short-run marginal cost. And this corresponds to figure 8.16 on the textbook. You can take a look at that. here we are going to describe the relationship between short-run and the long-run total cost curves. So we derived previously that the short-run total cost for different levels of capital, fixed capital, is q to the power of 4 divided by 4 times k bar plus k bar divided by 4. So I'm picking 3 specific values of k bar, and I'm writing down the short-run total cost for those curves explicitly. So I picked k bar equals to 2, k bar equals to 5, and k bar equals to 8. Those two corresponds to the 3 dashed line on the right, on the graph on the right. And last, we've also calculated the long-run total cost curve for this projection function and the input prices. That is q squared divided by 2. And I've drawn it as the solid orange line on the graph on the right. And you might have observed an interesting fact that all the short-run total cost curves lies above the long-run total cost curve. This is because the long-run total cost curve is actually takes the value that is the minimum of all the possible short-run total cost curves. So let's see on the graph on the right, I've put a 3 dotted black line that is very thin, but probably you can still see it. So let's look at this point here. Let's look at this point here. So at this point, the blue line, the blue dashed line, is the short-run total cost curve for k equals to 2, right? And the red one is for k equals to 5, and then the green one is for k equals to 8. And this blue line is the smallest of those 3. And it happens that the long-run total cost curve takes the smallest value of those 3. Now, if we look at this part here, the red line is the smallest of the 3 short-run total cost curves. And our long-run total cost curves happens to be the same as our red line over here. And lastly, if we look at this part, our green line is the smallest of those 3, and our long-run total cost curve happens to be the same as our green short-run total cost curve. And let me draw this on the graph. And I'm not, maybe using the pink color is helpful. So let me emphasize this curve over here. So I'm drawing along our blue line first because it is the smallest of the 3, all the way until this point. And after this point, the red line is below our blue line and is the smallest of all 3, right? So I am marking our red line over here all the way until this point. And until this point, the green line is actually the smallest of all 3. The red line and the blue line are higher than our green line. So I'm marking our green line over here. Oops. So beyond this point, I'm marking our green line. So what you can see, so if we compare this pink line, we are picking the points that is the smallest among the 3 at every point of Q, right? This is what this pink line does. And here I only drew 3 short-run total cost curves. You can imagine we can draw as much of them as we want for different values of k bar that is fixed in the short run. And this solid orange line is what we call an envelope of the short-run total cost curves. So the long-run total cost is an envelope line of the short-run total cost curves, because it takes the smallest value of all of those. So this pink line does not perfectly coincide with the orange solid line because I've only drawn 3 short-run total cost curves. But if I draw the infinitely many of them, and we take the smallest value of all of them, the orange solid line is what we get, and that is the long-run total cost curve. And let's look focus at a point here. For example, this is probably where we have the most obvious difference between our pink line and our orange solid line. And you can imagine that there is another short-run total cost curve that I didn't draw, which might look something like this. All right, there could be another short-run total cost curve that looks like this, and it will happen to touch this pink point. So it is below the blue line, the red line, and the green line that we have on the graph. And it is going to, well, at this point, the long-run total cost curve will take the value of our this brown short-run total cost curve that we didn't draw. So this is a graphical representation of the relationship between short-run and the long-run total cost curves. So again, this is figure 8.17 on the textbook. It is not drawn. I think the figure on the textbook is clearer in the sense that the gap between the curves are larger so that you can see better. The concept is the same. So this is a description of what I did just now. So for every fixed value of k bar, we can draw a corresponding short-run total cost curve. And for each value of q, we can look over all the short-run total cost curves, the value of those for different k bars, and we will find the one that has the smallest total cost. And this is what the long-run total cost curve will take the value of. So in a sense, in the long run, in the short run, the firm cannot adjust in the dimension of capital, right? But in the long run, the firm is also minimizing in this dimension of capital. We are picking the k bar of all different possible short runs, and we are finding the one that minimizes its cost in the long run. So the short run total cost intersects the long run total cost at point Q, where the following condition is satisfied. So in the graph, if you remember, the short run total cost for different values of k bar intersects our long run total cost at different points of Q, right? And for given k bar and Q, we have our solution. We have our optimal input combination in the short run. That is our L star and k bar here. So our L star depends on Q, W, R, and k bar, and we have the corresponding k bar. So the short run total cost intersects the long run total cost when this point happens to be also solving our long run cost minimization problem. And that is saying that our short run solution, the amount of labor that we are going to employ in the short run, happens to be the same as the amount of labor we are going to employ in the long run when we are allowed to adjust our capital. And also, the level of capital that is fixed in the short run happens to be the optimal amount of capital that the firm will choose in the long run. So when at this point, the short-run total cost will be the same as the long-run total cost. And at any other point, when this is not the case, our short-run total cost will be higher than our long-run total cost. As you can see on the graph, all of our short-run total cost curves are above the long-run total cost curve. All right. And we can verify this mathematically with the example that we have. I don't want to go into the math of it. It is going to involve a lot of algebra, and it's not too interesting to present. So you can, if you are interested, you can verify this yourself with the running example that we have in hand. All right. So here we are. This is an even more complicated graph that shows the relationship between our short-run average total cost and the long-run average total cost. So let me first introduce what is on the graph. So same as previous graph, I'm looking at three specific value of capital that is fixed in the short run. That is k equals to 2, k equals to 5, and k equals to 8. The blue long dashed line is the short run average cost, and the blue dashed line is the short run marginal cost when k equals to 2. So each color corresponds to a value of k, all right? And similarly, the red long dashed line is the short run average cost when k equals to 5. And the red dashed line is the short run marginal cost when k equals to 5. And lastly, the green one corresponds to k equals to 8. And I've also drawn two other lines, which are the solid lines, the long run ATC and the long run MC. And all those are drawn to scale, so they so we have derived the formula for our short run total cost. We've also calculated our short run average total cost and the short run marginal cost. So I was drawing the curves for three different values of k bar over here. And we also have the long run total cost, the long run ATC, and the long run MC. So I'm drawing basically those expressions on the right, on the graph on the right. Here I've also put three supplementary lines to help you see at what points do those curves intersect. So I'm going to mark a few points that's important. So the first one is that this pink point and the point over here. So at this point, the pink point, our short run ATC intersects our long run ATC. So at this value of Q, let's call this Q1. At Q1, our short run ATC intersects our long run ATC, and this is also the point that our short run MC intersects our long run MC. We can see that on the graph, right? And similarly, there are two more points over here. So looking at the second auxiliary line, if we look at this point, and if we look at this point, and if we call this point Q2, this is the point at which our second short run ATC, the red line, intersects our long run ATC, and that our short run MC, the second short run MC, the red line, intersects our long run MC. And lastly, the third point, it's over here and over here. So at point Q3, the green long dashed line, our short run ATC, intersects our long run ATC, and it is also the point when our short run MC intersects our long run MC. And you might have realized something interesting. So if I emphasize this part, the oops. So if you look at this brown part of the curve, okay, this is probably not a this probably doesn't look very good in the presentation. So what I want to say is that our long run ATC is also an envelope curve. So the long run ATC is also an envelope curve of the short run ATC. You can actually see it from this this graph, but it is not very easy to highlight it, especially close to this region. So let me mark another point where those two are. I'm not sure if you can see this brown point. So this point, this brown point over here, is the point where our below which the blue line is smaller and above which our red line is smaller, which corresponds to the short run ATC of two different levels of fixed capital in the short run. And here there is another point that is over here, which is when so if we draw an envelope curve of all the short run ATCs, the long run ATC is what we get out of this. So what I described in Word just now, I was saying that when short run ATC equals to long run ATC, that is Q1, our short run MC equals to long run MC. Those are the points. So at Q1, Q2, and Q3, we can observe that this statement is true. And another set of points that we want to mark, or the relationship we want to emphasize, is when the short run MC equals to the short run ATC. And if you recall, we have said that when they are equal, they are hitting the minimum point of our short run ATC, right? So at this point, point A over here, point A is the minimum point of short run ATC. So this is point A. This is the minimum point of our short run ATC when k equals to 2. And this is the point at which our short run MC intersects it. And we see that this point A does not happen at Q1, right? Q1 is when our short run ATC equals to our long run ATC. So the point at which those two intersects are not necessarily the point at which, so let me say this again, the point at which the short run MC and the short run ATC intersects is not necessarily the point at which the short run ATC and the long run ATC intersect. And this is what I wrote over here. And also that the MC and the ATC always intersect at the point where the ATC is at its minimum point. So this holds true for this point as well, and this point as well. So let me put an arrow to it. Hopefully it will become more visible. All right. And again, this corresponds to figure 8.18 on the textbook. It is presented differently with larger gaps of the curves between the curves. But I'm drawing this curve because I have all the corresponding equations behind it, right? So I'm deriving those curves from a real problem that we can define mathematically. And it's a trade-off between better visual presentation and whether I have the equations backing those graphs. So let's summarize what we did in this chapter. So we derived the long run and short run total cost curves as a result of our cost minimization problem. We similarly defined the concept of average cost and marginal cost, and we introduced an interesting feature, which is mathematically constructed to be true. So whenever our MC is larger than AC, our AC will be increasing. And whenever our MC is smaller than AC, AC will be decreasing. And MC intersects AC at the point where AC takes its minimum point. We've also introduced the concept of economies of scale, and we relate it to the return to scale of the production function. We say that the firm enjoys economy of scale when the average cost is increasing. So sorry, this is a typo over here. And again, I will correct it in the slides I upload. So this should be decreasing, and this should be increasing, all right? So a firm enjoys economies of scale when the average cost is decreasing as Q increases. And this happens when the production function has increasing return to scale. And I probably should have put this as well. For the production function. All right, because return to scale is a concept for the production functions. And conversely, the firm suffers from diseconomies of scale when the average cost is increasing as Q increases. And this corresponds to the case when the production function has decreasing return to scale. And this is the example, the running example we have been using throughout this chapter. And we also showed graphically that the long-run total cost curve is an envelope curve. So it is an envelope holding up the bottom part of all the possible short-run total cost curves. And the same holds true for the long-run average total cost curve.